being here. My name is Danilo, and I'm technical evangelist in Amazon Web Services. And the idea is that in the last few years, we've seen incredible advancement in how we can interact with computers and how computers can interact with the physical world. I'm thinking, for example, of image processing or speech recognition. And to learn how we arrived to this point, to learn something new, I usually like to start looking at the past. So do you know this picture? It's a picture that I'm abusing a little bit because I'm using it often. This is the London Tube in 1939 in March. And this is people counting by hand 4 million tickets to understand how the tube was used and to predict how it would be used in the future and plan for the future expansion of the underground lines. So when I see this kind of heroic efforts, it's really giving me like the energy to say, with the tools that we have now, with the tools that we have available today, we should really try to understand our data better to improve the user experience for our customers and our users. And this is a typical problem when you have lots of data, lots of information, and you want to build predictions. So in this case, we have 4 million tickets of the tube, and we want to predict the future usage. But it could be an audio file. I want to predict what's the speech inside this file, what's the intent behind this sentence in a text. And to do that, we usually create a model. A model is what can abstract you from the actual data and help you create predictions on new data that you never have seen, because you want to do predictions when you don't have old data to look at. And how can we build a model? That's where the field of machine learning is studying a lot. And if we continue to look back, in 1959, this is Arthur Samuel. This is probably the first guy who wrote a computer game with some sort of intelligence. So he wrote a checkers game that was able to play checkers. At first, he was interested in how you can explore the space of all the possible solutions, because that's the big problem in computer games. You have so many options, and you have to understand which one are good and which one are bad. But then he also had the idea of having computer games playing against other computer games so that you can learn and improve the strategy of a checkers game. And the result was a program, an application that was better than him in playing checkers. And this is probably one of the very first examples of machine learning. And machine learning is actually a broad field, and there are different subtopics. The most common one is supervised learning. And supervised learning is when you have you want to create a model, and you have labeled data that you can understand, and with the same information you want to predict. For example, you have the 4 million tickets of the tube, or if in the case of audio file, you have lots of samples of audio files with the text written down by someone that tells you what's the speech inside these files. And then you can start to use this information to create a model. Another field that is really interesting, it's unsupervised learning. It's when you don't have labeled data. You have lots of data, and you want to find the hidden structure inside this data. For example, if you're a large company and you have, for example, 1 million of customers, it's impossible to know all your customers one by one. So what you want to do, you want to start to do something like customer segmentation. You want to understand if some of these million customers have similar characteristics, so that maybe you can address those customers, those 100,000 customers, in a similar way. And it's quite common to do that. Another field is subfield is reinforcement learning, and reinforcement learning is a sort of the middle between the two. Is when you want to reach a goal, but you have a dynamic environment, so you can learn as much as you want, but you will never know what is going to happen. And an example of reinforcement learning is driving a vehicle, so self-driving autonomous cars, or even playing a game against a dynamic opponent, unless you explore all the possible solutions, all the possible moves of a game. In case of unsupervised learning, one of the most common use cases, and this is something quite historical because it's since the 80s that this is done, is clustering analysis. And clustering means that you have lots of data points, for example, the 1 million customers that you have with all the information you have on your 1 million customers, and you want to cluster those data points in groups. And you want also to find what's the right number of groups. So in this case, it's very easy. If we want to group this these bullet points is very easy visually to understand how you can create groups. But consider that normally the problem has millions of data points, and each data point can have not 2 dimensions like here, but hundreds or thousands of multiple dimensions. And you want to understand if there are hidden groups inside this large data set. Another interesting example of unsupervised learning is topic modeling. With topic modeling, you want to understand what are the abstract topics that are covered in a large corpus collection of documents. For example, an encyclopedia, but it can be also your emails. And usually the trick here is to look for infrequent words that are not normally used, that become more frequent in a document. That gives you an idea of the topic this document is talking about. And there's a very nice open source library for Python. It's called GemSim. So if you want to download your emails and do topic modeling and understand what are the 10 topics, the 10 top topics you talk about in your personal or business emails, you can do that quite easily with this library. With supervised learning, so when we have labeled data, these are the 3 kind of predictions that we want to build. Regression, when you want to predict a numeric variable. So for example, if you run a bike sharing scheme in a town and you want to know how many bikes will be rented tomorrow in this bike station, this is a number that you want to predict. It can be 0, 1, 100,000, and it depends on different variables, the weather and the period of the year. Very popular is binary classification, when you only want to classify data in 2 categories, usually true or false, or yes or no. And for example, most email clients, they already do that for looking for spam emails. So they automatically try to classify your emails in spam or not. Sometimes they don't work, and if you change manually the status of a wrongly classified email, this usually helps the engine to learn and improve better for the future. Normally, binary classification under the hood has a sort of percentage. So the algorithm will not say yes or no, but will say there's like 73% probability that this is spam or not. And you have to set a threshold, and that's something that is normally hidden by the consumer, but it's part of how you build the binary classification. Multiclass is something a little bit more advanced. You want to classify something across different categories. For example, sentiment analysis in the past was only binary. You wanted to know if a tweet or a comment on social media regarding your company or your brand is positive or negative. Now you can really look into, with the more advanced sentiment analysis engines, you can look into what kind of sentiment is behind. So it's this happy, sad, angry, confused, disgusted, surprised, calm, and so on. And normally, multi-class classification can be relatively easy built on top of binary classification. You remember, when you do binary classification, you have this percentage. So if you apply binary classification for all the category, is this happy or not? Is this sad or not? Is this angry or not? And then you take the one with a higher percentage, then you do a multi-class classification on top of a standard binary classification algorithm. And generally speaking, with supervised learning, the idea is that you need to create the model, and the term that we use is training the model, so that you create a model that when you apply the model on the labeled data that you have, on the data that you already have, you are going to minimize the error. And that seems simple, but actually there's a very big error that is easy to make. It is so you need to validate your engine, and by validation means that you need to be able to understand if the model that you create to predict the bikes or the users on the underground can work on new data, on data that it has never seen. So to do that, we have to avoid overfitting, and this is the underlying problem. So let's say that this is, for example, some numbers that tell me in the early hours of the day how many people is using bikes, shared bikes here in Milan. So from the early morning up to maybe the rush hour. If I want to create a model, I can create something very complex, like a polynomial here with a very good fitting. And I end up with a line like this that is fitting all my data points perfectly, and is predicting that in the very early morning, there's more people hiring bikes than later, maybe during the rush hour. So it's clearly wrong. And the idea is that probably a simpler fitting is much better than creating a very complex model for this use case. And this is because data points, in reality, when you collect data, they are never exact. There's always an error. So you shouldn't look for something that is absolutely correct. You should look something that fits very good to your use case. And the prediction that you get from this linear model are very different from the prediction that you get from the polynomial model, and are probably much better in this use case. So how can you avoid overfitting when you want to create and train a model with labeled data? The idea is that if you have lots of information, for example, the 4 million tickets of the underground, you don't use all the data for training the model. You use only 70–80% for creating the model, and you keep on aside 20–30% of the data as a validation set. So it's very important that this validation set, this data is never used during the training of the model. So you create the model, and then you test the prediction of the model on the validation set that it has never seen. And in this way, you can actually test if the model is capable of working on new data that it has never seen. So this is a very important step. But most recently, what happened, and probably one of the reasons why we are here in this room, is that there has been an advancement on a field that is not really new, but it's getting much, much more popular now. It's the field of the subfield of machine learning that is using neural networks to build predictions. And neural networks as a topic, as a concept, is not so new. So in 1943, at the time when the logical units of computers were physical, there was a physical AND and a physical OR, and you were connecting the AND with the OR with a cable. Someone already had the idea of building a threshold logic unit that was working similar to how the neurons of our brain work. So our neurons, if they get lots of signal, they fire. If they don't get enough signal, they stay silent. And this is something that you can do similar to an AND. So if you get a lot of connection, a lot of ones in binary syntax, then you fire a 1. If you don't get enough 1, you are below some certain threshold, you leave at 0. And this was the first use case of something similar to how our neurons works. A few years afterwards, there's this very important article from Frank Rosenblatt, The Principles of Neurodynamics, and he created a very formal model of how to simulate how a neuron works, and he calls this model the perceptron. And the model of the perceptron is this one. You have an input that is put into numerical format. So for example, if I want to predict the bikes, this will be the time and the day. I want to know how many bikes will be rented close to this venue. All these weights are weighted with some numbers, and these are the parameters that I need to find to fit the model. All is summed together and then goes to an activation function that is not linear, and usually as a sort of, it works like a sort of a threshold. So if you get a smaller value, nothing is getting out. If you get a high value from the input, then you get some sort of a output. Problem is, and then you can simplify this, putting everything together, and you have like this unit of perceptron that you can use. Problem is that in 1969, Marvin Minsky and Seymour Papert showed that this model was not powerful enough to model even simple things. For example, you can't build a XOR, an exclusive OR, with this perceptron. It's very limited. And strangely enough, lots of people lost interest in neural networks after this paper. Actually, someone had the idea, maybe we can do like in the brain. We don't have a single neuron, at least most of us, and we can connect more neurons together. And what happens is that you have multiple layers, and you have like an input layer where you give the input, then the output of this layer goes to other perceptrons, and so on, until you get an output at the end. The problem is that this creates lots of layers, a huge number of parameters, and you need something to train this model. And for the resources and the knowledge of the time, so in the 70s, this was very, very difficult. Someone started to formalize an algorithm to do that. It's called backpropagation, the idea of getting a wrong output, calculating the difference from what I want to do with my training, and then backpropagating this difference to do the tuning. Luckily, two things happened from the 70s to now. Moore's law allows our processors to become much, much faster. So in the 70s, we were in the range of the thousands of transistors inside a chip. Now we are in the range of the billions of transistors. So there's much, much more power that we can use to train this model. And also, video games happen. So how many people is playing video games here? So thanks, because thanks to your hard work, the GPU concept was invented, and the GPU allows us to train model in an easier way. Because while normal CPU have a limited number of very fast cores, like the fastest, the maximum number of cores that you get from an Intel processor, I looked a few days ago, it's now 28 cores. But if you get the latest version of the NVIDIA GPUs, this is the Volta generation that we just launched in our on Amazon on the EC2 P3 instances, you get more than 5,000 cores plus 600 and something tensor cores. Those are cores that can very quickly do some linear algebra computation, so multiply a small matrix, for example. And of course, all these cores are much slower than the core that you have in an Intel processor. But at the same time, there was an advancement in research to study how we can do backpropagation in a better way. And the algorithm that they found could be made in parallel, could be made it work in parallel very easily. So now we can use all these 5,000 cores in parallel to do the training. And normally a GPU is more than 1 order of magnitude faster than a CPU now. So if you use a GPU, if it takes 30 days to do a training with a normal CPU, it takes 1 or 2 or 3 days to do the same training with a GPU, to give you an order of idea. And what happened is also that how we use neural networks starts to be different. There are now multiple variations on the concept, and we probably lost the parallel with the biological neurons. So now neural networks are actually a stack of lots of nonlinear functions with millions of parameters. And what we found out with all the experiments that we ran is that they can solve lots of problems, and we still don't know why. So we didn't understand the mathematics behind the neural networks that we're using, but we know that they work very well. And it's important that these functions are not linear, because whoever studied linear algebra, you know that if you multiply only linear function, you only get a linear function, and then you can only do linear prediction. So it's the nonlinear fact of these functions that allows us to do strange prediction. And we use them for strange things. For example, for image processing, you can have the idea, okay, I take this picture, completely random picture since I'm from Rome, and you give this picture to the neural network with multiple layers, and you want to get a prediction and maybe wants to classify what's in this picture. This is very complex because you don't have, when you transform these pixels into numbers, you don't have any notion of locality in this pixel. You get a list of numbers. So it's very hard for the neural network to do something meaningful. So sometimes started with the idea of using convolution matrix. So convolution matrix, also known as image kernels in image processing, are a very simple idea. So you take a small matrix like a 3x3, 5x5, 7x7, and you move this matrix on top of all the pixels of the image, and for every pixel you multiply the pixel and the surrounding pixel for the values that are in this matrix. So this is an example of an identity, because I only take the central pixel and I completely disregard the neighborhood because I multiply them from 0. Of course, this is not an identity matrix. This is a different kind of algebra. But if I do something very easy, I change these values of the matrix, this very small matrix can find all the left edges in this picture. So now I can send some more meaningful data to the neural network, because I can send something that gives me the idea of how the 3D version of this picture works. And if I rotate this matrix, I can get all the different edges. And if I even give just random numbers, I still get a different perspective of the picture that can tell something different to the neural networks. So the idea is, okay, let's take a picture. Let's take a large group of random convolution matrix, and let's extract information. And all the parameters, including the numbers inside this matrix, will be parameters that I need to find and train to create the model. And in this way, this is the idea that is behind the convolutional neural networks. That is the way we do image processing now. For example, ImageNet is an open competition where academics and private companies, they can compete in doing image recognition. There's a large data set of pictures to recognize. And the error was around 30%. So it means that 1 prediction out of 3 was wrong when you were trying to classify an image. And this was completely unusable. In 2012, CNN, so the convolutional neural network, this approach that I just described was introduced, and the error dropped, and it's now, I think this year it's 2.25% the error of the top 5 classification. And this is very close to human error, because we can also make errors. And when you approach human error with something, then you are doing something that we can use without feeling it wrong, without feeling it not human. The idea is also that when you study the error with machine learning, the error is never linear. So when you move from an error that is above human error to the same level of human error, you transform something from unusable to usable. And this is the paper that describes this architecture. To give you an idea, there were 8 layers, each layer doing all this convolutional matrix stuff. At the end, you normally have some dense layer that is normal layer of neural networks. And there were 60 million parameters to tune. This to give you an idea of why we need lots of computational power to do this kind of training. And the year after, a guy had an idea, okay, now we trained this network in 2012. And the network automatically discovered the parameters of this small matrix. But what are these small matrices looking for? So we have multiple layers. I start to find ways to activate this matrix and see when they are reacting more. And he discovered that the first layer is actually looking for lines inside the picture, small patterns like linear, diagonal lines, and so on. At layer 3, we start to see strange things, like looking for orange round objects here in the bottom, for example. And if we go to other layer, we start to see matrix that look for face of dogs. Or even here at level 5, we see a matrix that reacts to eyes of birds. And this is completely self-trained. So the training found this in the pattern. And the idea is that in this way, we start to understand how the neural networks learn. So we have multiple layers. The first layer starts to look into more simple stuff and then more complex stuff. And this is now a field that is very hot, and it's the idea of transfer learning. So if we spend maybe 1 month or lots of energy to train a generic model, can we reuse something to a more simple, for a simpler model? For example, I want to just classify cat and dogs. I can just reuse all the parameters, maybe the 60 million parameters that I already found for a generic solution, and then change only 1 or 2 dense layers at the end and do only the training for that final part. So instead of 60 million parameters, I only have to find maybe a few thousand parameters. And that's the idea that is very hot right now, is how to optimize this kind of reuse. Actually, there's still lots of challenges in machine learning. For example, the scale is very huge. So you have lots of data. You need, for example, for images or audio, you need petabytes of data to process to create a trained model. And the training requires lots of GPUs or CPUs, depending what algorithm you're using. And then when you build the model, you want also to get the prediction very quickly, because if I build a model for bike sharing and then it takes 30 seconds to get a prediction, nobody will use it. You want a mobile app where you click and you get the prediction immediately. So this is another problem. To give you an idea of the scale, this is a work that we did with a university in the US. They were doing an experiment with topic modeling with a large corpus of academic magazines, and they used up to 1.1 million of virtual CPUs to do the training of this model. And in Amazon, we have lots of engineers that are focused on this topic since the first day we started in 1994. We have machine learning used in the fulfillment and logistics, so in the warehouses to optimize things like the delivery, like Amazon Prime, to optimize the search and discovery of products on the retail side. We try to optimize existing products, and we also try to launch new products.
Hello.
So the audio, I think you heard hello? Okay, so this is Alexa. I don't know if you ever tried it. It's not available in Italy, but it's a way to create a conversation with a device that can understand the intent of your request, and it's easily programmable and extensible. This is also another experiment we have. It's a shop that is available only in Seattle for Amazon employees. And it's a shop where you can go, you pick up whatever you want, and then you leave. There's no checkout. And the machine learning algorithm will automatically monitor what you do and create the bill for depending on what you got. And of course, when I was there, I tried to collect like 3 chocolate blocks, then drop 2, and do all the wordy things that you would have done, and everything worked very fine. And machine learning is used on AWS by lots of our customers, from the usual suspects like Netflix, Pinterest, Slack, to NASA. And what we are trying to do in AWS is to create lots of layers that can help any customer to use these advanced tools. So starting from the infrastructure, we can provide, for example, the last generation of the GPU with the NVIDIA Volta that are very powerful in computing tensors for training models. Then we have an AMI, so an image that you can use to create a virtual server on AWS that can automatically configure for you most of the common deep learning tools, such as Apache MXNet, TensorFlow. We recently added PyTorch that is very hot right now. It's Python only, but it's very promising. And We've seen customers doing amazing things with these tools. This is the University of Stanford, and with diabetes, diabetes can be one of the main reasons for blindness in grown-up males in the US. And to understand if you have some sort of diabetic complications, you need to look to the back of the eye, and then you need a very good doctor with a trained eye to look for the patterns in the blood vessels in the back of your eye. This is something that is very hard to do. You need a very skilled person. At the University of Stanford, they train a model that can act like a very good doctor, one of the best doctors. So you just need to take the picture and simplify this kind of diagnosis. This is probably the first medical imaging service that has been approved by the Food and Drug Administration in the USA, is Arteris, and they can use MRI scan to find early tumors even better than what a normal doctor does. Moving to easier topics, this is Huddle, and they can study the strategy of a sport game and give you advice on how to improve your strategy. So that they watch a lot of games and then can do that. This is too simple. It's a company that is between California and China, and they probably have one of the best engine for self-driving and autonomous cars. And they can work during the day when you have lots of information, but also they can work and have self-driving cars also during the night when you have much less information. This is an example of how they work. So they can do per pixel object segmentation. So here you see the green. The green is colored by them because it's recognized as being the road. And this is the first step for a self-driving car. You need to understand where the road is, and so that you can find objects that are blocking the road. And this is what they use this for. So on the top, you see the segmentation of the road, and on the bottom, they can assign colors because they can understand the distance of the objects so that the car can autonomously accelerate, brake, and change direction. This is Wolfram Alpha. Maybe you already use it. Wolfram Alpha is using AWS, and it's used by other services. For example, when you ask a complex question to Siri, Siri is actually, on the iPhone, Siri is actually passing the question to Wolfram Alpha. And I love this example because it's full of ambiguity. There's lots of ambiguity here. If I ask to Wolfram Alpha who recorded Pet Sounds, this can be a very strange question, but Wolfram Alpha can understand that Pet Sounds is a music album, and the artist is the Beach Boys. So this is the kind of reasoning that really can go beyond the normal pitfalls of ambiguity in machine learning. Pinterest can help you look for objects inside a picture to find similar ones and get more information. But as AWS, what we want to do is to make this available to any developers. So we start releasing high-level services that are available via an API so that you can include this in your next application. So we started with Vision and Amazon Recognition. So Amazon Recognition is a service that can help you look for what's inside a picture. So for example, here, normally you would provide a normal photo, a normal picture. Here I'm using the Mona Lisa. And if I give this picture, I get that this is a human, people, a person, it's art, it's painting, and it's a portrait. If you went below, it was also saying selfie, and I remove it because it was too much for me. This service can also do image moderation with different levels depending on the culture, and in this case, there's no moderation required. It can also look into the face. So this looks like a face, appears to be female. The age range is 26 to 43. So I went back to my books. This painting was mainly painted between 1503 and 1506. And then Leonardo worked for years, but for minor details. And Lisa del Giocondo, the subject, she's from 1479. So she was 24 to 26 years old during the painting. So we're overlapping the prediction. And I think it's quite amazing since since it's not a photo and it's even a picture. And she's not smiling and appears to be happy. So, you know, this is the key of the picture that was immediately found out by this feature. She's not wearing glasses or sunglasses. The eyes are open, the mouth is closed, and she doesn't have a mustache or a beard, of course. And you also get the landmarks. So if you want to put sunglasses on top of the face of the Gioconda, it's very easy because you get the position of the landmarks there. And she's a celebrity. In fact, the celebrity recognition recognized that this is Lisa Del Giocondo. And we have companies using this, for example, to analyze pictures on newspapers or videos from TVs to automatically find celebrities. And then I wanted to do a face comparison. And apparently, there's lots of copies of the Mona Lisa of Leonardo, lots of copies. And one of the copies that I recently saw, because I was lucky in Madrid in the El Prado Museum, is this one on the right. And this copy has a nice story because it was on display in the El Prado for 200 years and was thought to be a completely worthless copy of the picture. Then in 2012, they start to clean up the background. It was completely black before. And they found out that the typical Leonardo style background. And they start to think, maybe this is better than we have thought. They start to analyze. And now they think that it's the first copy that was probably done at the same time as the original picture by one of the students of Leonardo. And if you look at the perspective, there's the idea that probably it was painted at the same time, like 3 meters on one of the two sides where Leonardo was painting. So, and I tried to do a face comparison here, and I got 98% face comparison right match. So it's the same face. And just to be sure, since it was the first time I was using face comparison with a picture, I tried with another picture from Raphael, and there was no match here. So lots of companies are using this service to create interesting things. This is Binders in the Netherlands. They use this to automatically tag pictures in an asset management solution. So when you upload a picture and then you want to find out this picture for marketing, for example, you need to search, I want a picture of a guy on a bike with a cloudy sky. Normally you need to tag all the picture manually. They use recognition to do automatic tagging. And it's very convenient. After vision, we can go for speech. And here we have Amazon Polly. And Polly is the same voice that we use with Alexa, but supports 50 different voices and 24 languages, including Italian. And Polly is a very simple API. You give text or a speech synthesis markup language, and you get back the audio file in multiple formats.
It was nice to live such a wonderful life.
And this is how you use it. And as you saw, here there was a live and live that is written in the same way, but is pronounced differently, the verb and the noun. And Polly is actually analyzing the sentence, the meaning of the word, how the words are used, and can use the right pronunciation depending on the role of the word.
Nel mezzo del cammin di nostra vita, mi ritrovai per una selva oscura, che la diretta via era smarrita.
I think it's finished, okay? And this is an example of the voice in Italian. So you can use this. If you need a standard voice in your application, you can use it once, store the file, and the cost is 0. If you need dynamic voice in your application, you can use it. The cost is very low because there's like thousands of invocations every month that you have without any cost. And we have customers like Duolingo. They use this in their free application for language training. They switched last year, and they found that the voice was much more natural, and it's much more appreciated by their users. There's also the Royal National Institute of Blind People in the UK. They use this to transform all the text that they have, all the documents, into voice that can be listened by the people that has been affected by sight loss. And the last high-level service that we have is Amazon Lex. Lex, as the name suggests, is what's inside Alexa, if you remove the first and the last A. And the idea is to build a chatbot where you can interact using text or voice. So you can ask a question, what's the weather forecast? This can trigger a Lambda function, so a serverless function that we can execute without that you need to worry for the infrastructure. And then the output is automatically sent to Polly, and you get the output back. So you can use this using voice or using text. And Motorola Solution, they use this they showed this prototype last year when we launched the service. You know those like walkie-talkie that the police has in the US on their chest? They are actually very smart. They have a video camera. So they use this to look for missing persons. So if they can load the list of missing persons in the area, and then the camera is taking pictures continuously, and if a missing person is found, using the voice, they can say, hey, a missing person has been found where you are, and still using the voice, the policeman, so without moving the hands, can say, give him more information, send support, and interact without using the hands that are important for a policeman, that they are still free to use. So lots of different things. So depending on the level that that you want to have with machine learning. If you want to learn more, you can use the engines. They are not so complex to use, but still require you to understand how machine learning works, how to train a model, and keep you updated with the new releases. There are platforms and then services that are very, very high level, so any developers can just pick the service that they need and put them in their application. So I think there's never been a better time to build smarter apps. So I try to do that myself, and I try to build a do-it-yourself security camera. So I used to have a demo with a large Raspberry Pi. I upgraded my Raspberry Pi to a Zero so that I can move around easily in airport and get less attention from the security teams. And the idea is that you can build a camera, you can connect it to the cloud using our IoT platform, and then you can use Amazon Lex to enable your camera, take a picture, look for what's inside the picture. And since this is Lex, you can use a chat or you can use voice. And Lex can be integrated in a smartphone application. We have a tool, it's called Mobile Hub, that can automatically create an Android, iPhone, or a JavaScript application that you can use for using your bot and other things. It can be integrated with Facebook, with Slack, with Twilio if you want to interact using SMS, and can also be exported with Alexa so that you can reuse what you did with Alexa. So the project is open source, is on GitHub here. I actually open sourced it today during the main keynote. I hope I didn't left any security data inside some files, but it should be clean. So let's try to use it. So here I have I have my Android Studio and an emulator. So let's start from clean here. And this is my Raspberry Pi, and I already connected just for debugging here. And we get some logging here to see how it works. So let's start taking a picture. So I'm using the voice. So I go to voice demo, and I can say, take a picture.
A picture has been taken.
And I don't hear what it say, but it worked. So someone says, okay, or it didn't work. So you see now the picture has been uploaded, and you already see what was found here in the picture. But I can say, describe what you saw.
There is computer keyboard.
Did you get
keyboard,
something?
Computer,
okay.
LCD
And then I
screen.
can also take a selfie. This is mandatory. Use the camera. I saw it.
A picture has been taken.
And my hand was shaking like hell. So let's see if it could recognize something, because, okay, it found something. Confused, angry, and sad. It's
Sorry,
good, female.
Can you please repeat that?
Usually, this is sort of fun. If you shake the camera, it smooths the skin, and then it's much easier that it finds the person to be female. So let's try to teach. Oops, this is. Let's go. It's quite difficult for me to follow because I don't hear. So let's go to text for now, and let's say this is Danilo. Are you ready to take a picture? Yes. Let's try to be less sad. Okay, the picture has been uploaded. So in this way, I can teach a face to my security camera. So the camera is capable already of finding any celebrity. So if any famous actor is trying to steal something in your house, it will be caught immediately. But now it knows also my face. And now I can take another picture. Like, take a picture, please. And now it's looking for a face. Happy is more than sad, so it's good. Now I'm male back, okay. As I said, the shaking hand is always something wrong. And if we go, we already see here that it found with 99.99 confidence that that I'm here, but I can still ask, and we can go back to voice now. Text to voice demo. What did you see?
I have seen one face, a happy male face, aged 38 to 59. One is Danilo.
Okay,
There's
great.
also people,
Okay, this was just a
person,
quick
female.
example. The code is like 30 lines of code. What is nice is this: I'm using all fully managed services, so Lambda function, Lex, AWS IoT here. This deployment, it is a prototype, it's running currently in 2 AWS regions in the US and in Europe. In each region is replicated across at least 3 data centers and that they are running in parallel. There's automatic scalability, so I can use it once per month or 1,000 times per second. I don't need to change my application. And I only pay for what I do, and there's a huge free tier for when you start. So this is just to give you an idea of how you can very easily build something on the AWS. I hope it was interesting, and I'm very happy to take some questions. So, come facciamo per le domande? Any question? Otherwise, I'm available in different languages after the presentation.